So let's see. The last thing that I'll describe in this, in my slides, is the graphical determination of activation energy. And so we can determine activation energy experimentally, which you often have to do because that's really hard to do theoretically. And so you can do this by measuring the rate constant at several different temperatures and using this version of the Arrhenius equation. So it's this same version that I showed you right here, but now we've done some algebra. And this algebra ends up being y equals negative mx plus b. So it's another line. So let's look at that in more detail. So once again, we have our y equals negative mx plus b. Identify the slope in the y-intercept. Okay. Well, the y-intercept is going to be the natural log of this frequency factor. Okay. Beautiful. Which is given right there. The slope, so as you can see now on this x-axis, it's been graphed as 1 over t. So that means if my x-axis is 1 over t, my x scale is given by 1 over t, and now my slope of this line, so we can say slope equals negative EA divided by r. And so if you do some algebra here and multiply r by the slope and include that negative sign, that will give you the activation energy. Okay, so a little bit more details on what all this stuff means. And I want to go back now to this version of the Arrhenius equation, K equals A E to the negative EA divided by RT. So what is this A term? What does that give us? Well, what happens, so suppose we have EA equal to 0. What would we get? Okay. Well, if EA equals 0, I'll continue this on down here, we would have K equals A, E to the 0 power. And of course, that'd be 0 divided by RT, but we recognize 0 divided by anything is 0. And hopefully we also recognize E raised to the 0 power is 1. So in this case now, if we had 0 activation energy, K is the frequency factor. And what that means now, if we have no activation energy, I'll back up here, then we're talking about a diffusion limited reaction, right? The rate limiting step is just how long it takes for them to collide. They collide, they instantly react. So this would be an EA equal to 0 or very closely equal to 0. And in this case, our rate constant K would equal the frequency factor. And that frequency factor is how often a collision happens, which is pretty cool. So now I want to show you this thing that I've got down here. So this is the program Mathematica. So this is some pretty advanced stuff. This is what we do in my CHEM 361 class, which is a class entirely dedicated to kinetics and thermodynamics. And so my senior chemistry majors will write these programs to understand kinetics theoretically. So here's one example of a reaction I wanted to show you. And let's go to this, this activation energy equation. So here, just as a fictitious reaction, 2A reacts with 2B plus C. It's a second order reaction, so that's given to you right there. You can see there's all kinds of input parameters. The initial A we can call 0.01, and the initial B and C we can call 0. We're using this Arrhenius equation here to calculate a few things. And when we look at it, we can see this is what our reaction profile looks like. So here's the A molecules, and you can see they're decaying because they're reacting away. And here you can see B and C are produced. And of course, B is produced at twice the amount of C because of the stoichiometry, right? But what's really cool about this program, and I know there's a lot of gross looking programming languages in here, we can do this thing called manipulate, where now I can look at how this concentration versus time profile changes when I change these input parameters. So the first thing we'll do, we've got temperature at 1 Kelvin. That's not realistic. Let's make it something like 298. There we go. We know that A equal to 1 is also not very realistic, so I'll just kind of put a random number in there. And here now you can see I've got 0 initial concentration of A. So let's put some of that in there. And so you can see now that's changing my scale. And this is a really fast reaction because you can see there's like no B created, or rather we don't see any A. It just looks like B and C are created instantaneously. So now let's slow down that reaction. And I can slow down that reaction by decreasing this frequency factor. So we'll just keep this on like some easy to use number, like let's say number 1, okay? So you can see now with a low frequency factor, the reaction really slowed down. So what happens if I increase the activation energy? So you can see I've got 0 activation energy. So now if I start to turn up this activation energy, you can see that I can basically completely turn off the reaction, right? I've made the activation energy too large for anything to react. And if I go back and decrease that, you can see as I make the activation energy smaller and smaller, the reaction gets faster and faster and faster. And we realize the reaction is getting faster because we're seeing A deplete over this time interval, and B and C are created over that time interval. Okay. So now let's say I go up to this really high activation energy. So that's too much energy for this to react. Well, what could I do to make it react? Well, I could increase the temperature. So now if I increase this temperature past 298 and I keep taking it up and up and up and up and up, so you can see I had to take it up to about 1,000 Kelvin for this 30,000 joule activation energy. But you can see here I did get a little bit to react when I cranked the temperature up on this thing. And so, of course, if at this very high temperature, I could somehow turn down the activation energy even further, you can see I can really get that to react much faster. And so now let's say with this 9,600 joule per mole activation energy, you can see that changing my temperature has a lot more of an influence, right? I can make it colder, it reacts slower, I can make it faster, or I can make it hotter, and it reacts faster. So of course, this is all theoretical, but this gives us a good place to start understanding our kinetics.